welcome back. In today's lecture, we're going to talk about feedback systems and internal stability. Okay, so we'll start off by talking about some basic facts about feedback loops, and then after that, we'll discuss what it means for a feedback loop to be internally stable. Okay? All right, so I want to start off by giving some sort of general motivation for the feedback loop and kind of where we are in the class at the moment. Okay? So far, what we've done is we've introduced some basic design tools, right? Design tools. So for example, this is something like state feedback, where in static state feedback we had something like u equals k times x, right? Just a linear gain times our state x, and we showed under certain conditions we can get stabilization, right? We also had output feedback, right? So this is where we examined like an A minus LC kind of expression along with a Leuenberger observer. Then after that, we introduced optimal control. And this was in the case of full state knowledge, right? So basically what we've done is we've introduced a couple of basic design tools, right, that just say, okay, in the case where I have full knowledge of my state, this is how I can design a controller, right? In the case where I have partial knowledge of my state, maybe this is how I can design a controller, right, using this observer idea. And then finally, in the case where I have full knowledge of my state, this is how I design the best possible controller, right, the optimal controller. We kind of looked at this through the lens of LQR, right, which is kind of this, you can maybe say canonical optimal control problem for an LTI system. Okay, so what's next? Well, let's kind of think of some gaps that we have kind of in these control strategies that we've introduced so far. Okay, so one gap is that we've only considered one basic method of doing output feedback. Right? We only consider this Leuenberger observer. We haven't considered any more kind of sophisticated feedback arrangements, right? Now, second, kind of along these lines, we haven't discussed optimal output feedback. Optimal output feedback. Okay? So to kind of set the stage for these two things, we'll study more general feedback loops, okay? So what we're going to do today is we're going to kind of set the stage for discussing other methods of designing output feedback controllers and maybe other methods of designing optimal output feedback controllers, okay? So we're going to kind of lay out a general structure that is very common and encompasses a lot of different problems. And then over the course of the next two lectures, we'll kind of study some basic properties of this structure, okay? So we're not going to treat this idea of optimality in full detail in this course. If you're interested in that, you could take a course in robust control. That'll typically explore some of these concerns. But we're really just kind of set the stage and talk about the big picture important ideas here, okay? All right, great. Let's get started. All right, so my first question is, what does a good general feedback loop look like? Okay, so maybe take a moment and maybe brainstorm something that you've seen in your previous classes, right? And something that you might have seen before. So in a first course in control, maybe you saw something that looked like a controller block K going into a plant P, right, which outputs some value Y, and then maybe this signal Y is then fed back into this junction over here, right? We pass in a reference and then we kind of subtract where we were for Y, and that gives us our feedback loop, right? So this is common configuration, but maybe not general enough, right? Enough, okay? So here we only have a single output, Y. Your controller K is forced to take in this R minus Y signal, and so on, right? We also have no disturbances slash noise, and so on and so forth, okay? So what we'd like to do is we kind of like to come up with a really general feedback arrangement that kind of addresses all of these concerns, but at the same time, is still general enough to encompass this basic feedback system, okay? So what I'm going to do now is I'm going to define something called the general feedback arrangement, okay? And this is going to be a really general class of feedback system that we'll focus on in the next couple lectures. All right. So first, I'm just going to go ahead and define what this general feedback arrangement is, and then I'll kind of discuss its structure just later, okay? So definition, general feedback arrangement. Okay, so before I state this definition, just remember what we're going to consider is interconnections of LTI systems, right? So we're going to model the system which we want to control as an LTI system. And then as we saw in the kind of Leuenberger observer lecture, it's actually beneficial to model our controller as an LTI system as well, right? Which takes in an output measurement and then returns the control input as its output, okay? So how are we going to define this? Well, a general feedback arrangement consists of two LTI systems. One, G equals A, B, C, D. This is called the plant, okay? So this is the system that we want to control. So this terminology plant comes from kind of conventions that, a lot of control was kind of developed for power plant regulation, okay? So we have one system, G equals A, B, C, D, called the plant, and another system, K equals AK, BK, CK, DK, and this is called the controller. Okay, and these two are in the feedback structure that kind of looks like the following, okay? So we're going to have a system G up here. So this is our plant, right? This is a system we're trying to control. We're going to put this in feedback with this controller block, which we call K, right? So remember, each of these is an LTI system, right? K isn't just a static gain here. It's actually an x dot equals AK plus BK times this output measurement, right? Okay, so coming into G, we're going to have two different things. First, we're going to have a disturbance term, W, okay? Then we're going to have a term Z, which comes out like this. Then we'll have a measurement Y, which will pass into our controller, right? And then finally, we'll have a control input U, okay? So what do each of these terms represent? Well, W is something called the exogenous input, okay? So this is, for example, environmental disturbances, such as wind, maybe we have unknown force, and that sort of thing, okay? So those are inputs to this plant system that we don't actually have control over, all right? So that's W, right? Now our system U, our input U over here is our control input. So U is the control input, and this is just our standard input, okay? So this is the signal which we can control, all right? So this is what we can actually use to influence the behavior of the plant system, okay? Now Z is called the controlled output, right? And this contains everything that we kind of want to control in our system. So maybe, let's say, a common goal in these sorts of problems is we want to drive Z to 0. Maybe Z represents some component of the state that's particularly meaningful. Maybe it also includes a component of the input. If we want to kind of make Z small, then that means that we're asking for small inputs and maybe a small component of the state as well. It's really just anything that kind of draws from this information contained in G, right? And then finally, Y is the measured output. Okay, so this measured output is now measurements of the system, okay? So this is anything we could use actually for control design, all right? So the nice thing about this general feedback arrangement is it kind of distinguishes between these different inputs and outputs in the system, right? And it says, okay, maybe I have two separate inputs to the system, one of which I can control, right? That's coming from my controller block, and one of which maybe represents unknown forces which I cannot control, right? That's W, okay? Now, at the same time, we kind of like to separate between our two output variables, right? We have our controlled output, which contains variables we're interested in controlling, and finally our measured output, which is what we can actually use for control design, right? The signal that we exactly know, all right? Now, it's possible there could be some overlap between these, right? They don't have to be different. Okay, so now that we've kind of set up this system, I just want to talk about a nice way of kind of partitioning these A, B, C, D matrices that really makes it nice and clear what these state and output equations are for each system, okay? So first I'm going to talk about what the plant system is. So the plant system will be the following, okay? So we'll say that G is represented by the following state and output equations. So first, I'm going to go ahead and write out the state equation. So I'm going to have x dot of t equals a times x of t, standard, right? But now instead of just having one b, right, I'm going to have a b1 and a b2, which makes up my entire b matrix, right? Because now I have two inputs to my system, okay? So I'm going to have a plus b1, b2 block matrix, right? Multiplied by a, that's just a w of t, not a w1, multiplied by w of t and then a u of t, okay? So w comes into the first input channel and u comes into the second input channel, right? Now these are all just vectors, right? But kind of makes it convenient just to split up what w is doing and what u is doing, okay? So that's our state equation. Now for our output equation, we have two outputs, right? We have a z of t and we have a y of t instead of just the usual 1y of t, okay? Now likewise, we'll just kind of split this up into blocks, okay? So we'll have a c1, a c2, multiplied by x of t, which makes up our entire C matrix. Then for D, we'll have a d11, d12, d21, and a d22, all multiplied by w of t and u of t, okay? So this gives me my state and output equations for my plant system. Usually we just find it very convenient to kind of partition in terms of what's coming from my exogenous input W and what's coming from my controlled input U, okay? Likewise, we like to split into controlled output and measured output to really make clear what's going on with our system, okay? All right, so that's what our plant system is. What about our controller system? So 2, we have our controller system. And our controller system is just going to be a standard LTI system, right? So what's it taking in? Well, it's taking in y as its input, right? And it's returning u as its output, okay? So kind of like what we had earlier in the course, we're going to have an x dot of k is equal to ak times xk of t plus bk times the input to this block, which is a y, right? Multiplied by y of t. And then we're going to have the output of this block, which is a u of t, will be equal to a ck times xk of t plus a dk times y of t. All right? So this is our controller system. So just as a quick side note, I know usually, right, the input to our system, the input to our system is a u and the output is a y. For the controller block, it's the other way, okay? Because a y is coming into this block and a u is coming out of this block, all right? So just be sure, just to kind of make that distinction in your mind, okay? What else are we going to do? Well, we're just going to make some basic regularity assumptions, right? This is an I/O model, and if we're working on input-output models, it's usually nice to assume that the internal state space system has some sort of stabilizability or detectability assumptions, right? After all, something that we discussed earlier in the course is, from the I/O perspective, the controllable and observable part of the system are kind of the only things that we could actually see, right? So as a result of that, we could just make a nice, easy generalization to stabilizable and detectable, okay? So this is stabilizability and detectability. Stabilizability and detectability. And what we're going to do is we're going to assume AB and AK, BK are stabilizable and detectable. Just stabilizable. And that A, comma, C and AK and CK are detectable. Okay? So as a quick side note, why can we do this? Well, we can assume minimal realizations, right? So these are controllable and observable realizations, right? Because those are the only things that appear from an IO perspective. Since the feedback arrangement is an IO model, okay? So as opposed to having a minimal realization, stabilizability and detectability is an easy generalization of minimal realizations, okay? Which refers to controllable and observable. Okay, fantastic. So this is kind of our basic feedback arrangement, right? We have a plant G, which outputs a controlled output Z, a measured output Y. It passes the measured output into the controller block K, right? K can then use that to compute a control input U, which is passed back into the plant, okay? So this feedback loop kind of occurs. And what we could show is that this feedback loop is actually extremely general, right? In fact, this encompasses this kind of simple feedback loop that you might have seen in your first course in control, right? So it's a kind of nice exercise to show that this really simple loop up here kind of falls into this general arrangement down here, all right? Okay. All right, so what's next in our study of these feedback arrangements? Well, something that you might have thought of is, okay, we're interconnecting all these different feedback systems. How do we actually know that these feedback systems are well defined, right? Does this interconnection necessarily make sense? Well, kind of think about it for a sec. Maybe something that could occur is we can get some conflicting information happening between this plant system and this controller system, right? We have a set of algebraic equations in here, right? Z of t, y of t, w of t, u of t, and this u of t equals, some function of y of t as well. Maybe what could happen is we could end up with conflicting information in these two kind of output equations, okay? So what we want to make sure of is that, we don't get any sort of ambiguity in the definition of these state and output equations when we make this feedback connection, right? And in order to do that, what we'd like to really make sure we have is unique solutions to our feedback interconnection system for all time, okay? So, if these solutions are unique, then it'll kind of make sense to talk about this feedback system as being well posed, all right? If they're non-unique, then maybe this feedback system is not really very well defined, right? Because, there could be any number of signals going through each of these channels, okay? So let's go ahead and state a definition for well-posedness of a feedback system. This brings us to a definition, and this is a well-posed feedback arrangement. Okay, so what we say is that the feedback arrangement, or just rather a feedback arrangement, is well posed if its state and output equations have unique solutions for all admissible inputs. Okay, so this is the W signals, right? Inputs W, and all initial conditions. Okay, so how are we going to make sure that we get kind of unique solutions for all admissible inputs and all initial conditions? So how do we check this? How do we check? Well, let's take a look at what we had with the state and output equations up here, right? We seem to have a relationship between y and u over here and a relationship between y and u over here, okay? So if we want to figure out if we get unique solutions, then we should make sure that we get unique solutions for y and u out of both of these equations, okay? So what we're going to do is we're going to try to set up a linear system to solve for y and u, and then depending on whether that linear system has unique solutions, we'll be able to make a claim about well-posedness, okay? So let me write that down real quick. So the idea is we get y and u showing up on both sides of the state and output equations. Okay, so let's solve for y and u and determine when we get unique solutions. Okay. Then once we have these, we can simply plug into the state equations. Okay. State equations and get unique solutions. So it really should be enough to make sure that we get, kind of unique solutions for y and u, right? Once we have those, we could just go ahead and plug into the state equations and then just apply our standard existence and uniqueness theorems once we have that, okay? So what I'm going to do is I'm going to go ahead and state a proposition that says effectively when we can uniquely solve for these y and u signals. And then I'll kind of go ahead and derive those conditions and just kind of prove that those are actually sharp, okay? All right. So let me go ahead and state a proposition, which is well-posedness of the feedback loop. Okay, so what we say is that the general feedback arrangement is well-posed if and only if either of the following hold, okay? So either one of the following conditions is in fact equivalent to the feedback arrangement being well-posed, okay? All right, so I'm going to state two tests. First, we're going to have a block matrix test, okay? And this test is effectively going to be that the matrix I minus dk minus d22 and I is non-singular. Okay, so this matrix is invertible, in other words, right? Now here, let me draw that a little neater. I just want to clarify this dk and d22 matrix. These are the matrices that just come from our system representations up here, okay? All right, so that's the block matrix test. And then our second equivalent test for determining well-posedness is that it's going to be called the Schur test, all right? I'm going to just kind of remark on this name just in a sec, but this is going to say that the matrix I minus d22 dk is non-singular. Okay, so just as a quick side note, Schur does not refer to an eigenvalue condition here. Rather, it just refers to a determinant identity. Okay? So there's going to be a formula called the Schur formula for the determinant of a block matrix, which is effectively where this derives from. Okay? So it's the same name, Schur, as the eigenvalue condition, right? Where all the eigenvalues belong to the unit disk in the complex plane, but it's not in fact related to that. Okay? So only in name. All right, fantastic. Let's go ahead and give this a proof. So once again, our strategy is solve for u and y and plug into state equations, okay? So I'm going to start by proving sort of test one, which is this block matrix test, and then we'll see where we go, okay? So what I'm going to do is I'm going to write out the state and output equations of the full system, right? So I have an x dot equals ak plus b1 times w plus b2 times u. Then for my controller, I have an xk dot equals this akxk plus bky, right? Or y of t. Now, for my output equation for my first system, I'll have a zy equals c1, c2 times x plus this d11, d12, d21, d22 times this w and u, okay? And then finally, I have a u equals ck xk plus a dk times y, okay? So what I want to do, remember, uniquely solve for y and u, right? But I have them on both sides here, okay? So there's a little bit of work that I need to do. Okay, so what are we going to do? Well, let's go ahead and isolate y and u, and we'll see what we find, okay? So let's put these together in a vector. So I get u, y will be equal to this ck xk plus this dk times y, right? And then y is equal to a c2 times x, right? Just reading off the equation up here, plus this d21 times w plus a d22 times u. Okay? So what do we do now? Well, let's just go ahead and bring all our u and y terms to one side, right? What we find is that we get a u minus dk times y, right? Where I'm pulling this dk term over, so this guy. Then if I pull this d22 times u over, then I get a y minus d22 times u will be equal to a ck times xk, and then a c2 times x plus a d21 times w, right? And then what I'll do now is I'll just kind of factor out this u and y, okay? So if I factor out the u and y as follows, what's the matrix that I get over here? Well, I get an identity, right? Because I just have an appearance of a u. Then I get a minus dk, right? Then I have a minus d22, and then finally another identity over here. And this ends up equaling a ck times xk, and then a c2 times x plus a d21 times w. Okay? So what happens? Well, if this is invertible, or rather, I can uniquely solve for u and y if and only if this is invertible. Okay? Because then I just invert the matrix, pull it over to the right-hand side, and then plug those u and y's back into my state equations over here to get kind of a unique solution to everything else. Okay? So provided I'm able to uniquely solve for u and y, I just plug that unique solution back in, then I apply my standard linear system's existence and uniqueness arguments. Okay? All right, so what we see is that, test 1 in fact holds, right? This matrix I minus dk minus d22i being non-singular is in fact a sharp characterization of being able to uniquely solve for all these different state and output equations, right? Okay, so that goes ahead and gives us well-posedness, right? Now, what are we going to do for case 2? Well, for case 2, I'll just prove it's equivalent to test 1, okay? So what we want to do is we want to figure out a test for invertibility of this matrix I minus dk minus d22 and I, okay? So this brings us to a side point on what's called Schur's formula. And Schur's formula for the determinant of a matrix states the following, that if a matrix A is invertible, and you want to take the determinant of this block matrix, A, B, C, D, then given this assumption of invertibility, this is equal to the determinant of A multiplied by the determinant of D minus CA inverse times B, okay? So basically what we're going to do is we're going to go ahead and apply Schur's formula to this block matrix we derived in part 1, and that'll effectively give us condition 2, the condition 2 of this rule. Okay, very cool. So let's go ahead and apply this to figure out the determinant of I minus dk minus d22 and I, right? So clearly the identity matrix is invertible, right? So this is equal to the determinant of the identity, which is just 1, determinant of the D matrix in this case, which is the identity, minus this C term, which is this negative d22, then an A inverse, which is still the identity, right? Because I inverse is identity. And if we perform all this multiplication out, what we get is these minuses cancel, and we still end up with another minus due to kind of this formula term over here, right? So our result is an I minus a d22 times dk, okay? All right, now this, if we just eliminate this determinant of the identity, is an I minus d22 dk, okay? So what we find is that the determinant of this big block matrix, which we derived in part 1, is invertible if and only if, is non-zero if and only if this determinant is non-zero, right? So we conclude the system is well posed if and only if I minus d22 dk is non-singular, right? Since that's equivalent to its determinant being non-zero. Okay, so that gives us a sharp test for well-posedness in terms of these different system matrices, okay? All right, So one kind of nice thing that you'll notice about this test is that if either dk or d22 equals 0, we are guaranteed well-posedness, right? So these D matrix terms in our state space systems are really what are causing us the problems, right? This is the only place where these algebraic problems could kind of arise. Okay, so just as a quick side note, usually in a first course in control, well-posedness is probably not something you'll discuss, and part of the reason for that is that you assume that all transfer functions that you're working with are going to be strictly proper, and strictly proper will correspond to the case where a D matrix is 0. Okay, so it's for that reason that a lot of the times when you first encounter these feedback systems, this isn't really a concern. Okay, all right, fantastic. So this concludes the first part, kind of on this basic feedback structure, right? This so-called general feedback arrangement and kind of its well-posedness, right? Some of its basic properties. Now what we're going to do next is we're going to discuss something called internal stability, all right? Okay, let's get started. So I want to start off by talking about some basic motivation for part 2, which is internal stability, okay? All right, so let me start off by asking the question, what are our basic goals when designing feedback systems? Okay, I'm going to take a moment to think about this question. All right, maybe some things that are desirable to get out of these general feedback arrangements which we discussed. Okay. All right, so I'll assume you've given that some thought, right? Maybe something that you came up with is stabilization, right? Like oftentimes we like to say that we have like a kind of stable system, right? Now in the context of kind of this general feedback arrangement, maybe what we're interested in is keeping z small in the presence of an unknown disturbance w, okay? This is also something that we're interested in, right? This might be kind of valuable. But, how does this relate to this idea of stabilization, right? My question is, can we have one but not the other? Right? Can we keep z small in the presence of w without having stabilization, right? Or does stabilization imply that z will be small in the presence of w? Then my second question is actually, what do we mean by stabilization? In context of the general feedback arrangement. Okay? So to answer these questions, let me kind of give you a simple example, right? So let's say for a moment that the transfer function between, let's say, my disturbance term w and my output term z is identically 0, right? So, just kind of constructing a really simple scenario here, right? Not necessarily paying attention to all of the nice assumptions that we made earlier, okay? So how could this happen? Well, maybe something we can have is that the input term, right, all the way up here, this B1 term could be 0, and maybe C1 could be 0 as well, right? Maybe D11 is also 0, okay? So let's say maybe we have B1 equals 0, D11 equals 0, and then C1 equals 0. Something along these lines, right? Well, does this mean the rest of the system is stable? Right? We seem to have a perfect relationship between W and Z, right? We pass in any sort of disturbance term that we want and we still get 0 as our output, right? This seems pretty fantastic, right? But this, doesn't turn out to have anything to do with the rest of the system, right? My internal states could be blowing up, right? So the states of the system could be completely unstable. Completely unstable. Okay? So even if I get a perfect behavior between W and Z, inside my systems, right, if I actually peer inside and look at these state vectors and what they're doing, right, those state vectors could be going completely unstable, right? They could be exploding to infinity. Maybe my input term could be exploding to infinity as well, right? All these different things could be happening, okay? So in general, it's not enough to just ask for good I/O behavior, okay? So as a basic requirement, we should seek out state behavior that is stable. Okay? So, eventually good I/O behavior might be sort of our end goal in this control design process, but we shouldn't have this good I/O behavior at the cost of our internal system dynamics being completely unstable, right? So kind of as a basic requirement for our feedback system, we're going to set out something called internal stability, all right? And what internal stability is it effectively just says the full state vector of my system, right, including the state vector of my plant and the state vector of my controller, needs to be globally exponentially stable, okay? So let's go ahead and set that definition out. So this is a definition, which is internal stability. Okay. So what we'll see, what we'll say is consider a general feedback arrangement which interconnects a plant G and a controller K. All right. So we say that the feedback arrangement is internally stable if for a disturbance W, which is identically equal to 0, the full state vector, right, which is x and xk, is globally exponentially stable, okay? So I know typically we don't mention a state vector being globally exponentially stable. What I mean here is that when W equals 0, our full system dynamics is globally exponentially stable. Okay, so if we write x dot equals a big matrix A times x, xk, then that should be a globally exponentially stable system. Okay? All right. So again, internal stability is effectively just the requirement that the internal states of our system should not blow up in some sense, right? Now, even if we pass in some sort of small bounded input, internal stability, based on what we've seen about stability before, should at least give us a boundedness condition on these internal states. All right? Okay, fantastic. So how are we going to develop a test for internal stability? This is our next job. So question, how to test for internal stability? Wait, actually I should mention one other thing over here. So this is one component of it, and then also the feedback system must be well posed. Okay? Since without this well-posedness condition, solutions of our system is not really something we can talk about, okay? So we require well-posedness and global exponential stability. All right, let's get back to it. Okay, so how do we test for internal stability? Well, first we could test for well-posedness. So this is this test that we had developed above, right? We had this nice I minus D22 dk invertibility test, which gave us a sharp characterization of well-posedness. What else can we do? Well, after that, to actually test for this stability condition, we could find a matrix A closed loop such that we get x dot, xk dot is equal to A closed loop times x and xk when W is identically 0, okay? And depending on the eigenvalues of A, right, if it's a continuous time system, we need the eigenvalues of A to be in the open left half plane, right? In other words, we need ACL to be Hurwitz. If this condition is satisfied, then we should have internal stability, right? Okay, so let's go ahead and state a test for internal stability. So first, what I'm going to do is I'm just going to go ahead and write out the test and what this closed loop matrix is. Then we'll go ahead and derive it. All right? Okay. So what are we going to say? Well, we're going to say theorem, which is a test for internal stability. We're going to say that the general feedback arrangement actually specify connecting G and K is internally stable if and only if, first, this matrix I minus D22 dk is non-singular, right? It's kind of what we had established before. And the matrix ACL, or A closed loop, which is equal to this big matrix expression A00 AK plus a B2 00 BK multiplied by an I minus DK minus D22 and I inverse. Notice that this inverse existence is justified by the fact that I minus D22 DK is non-singular, right? This is the Schur test we had talked about before. Finally, multiplied by 0, CK, C2, and 0. This matrix is Hurwitz. Okay? So just as a quick side note, you can develop all of this theory as well for discrete time systems. So for discrete time, we would require ACL to be a Schur matrix, right? Instead of a Hurwitz matrix. Okay, fantastic. So how are we going to go ahead and prove this result? Well, we're going to do that strategy that we just kind of sketched out above, right? What we're going to do is we're going to set W to be identically 0, and then we'll go ahead and solve for our state equations involving x dot and xk dot, okay? So let's go and give that a try. All right. So our proof of this, well, we're actually going to be able to use some of the things that we just derived above, right? Because above we just said, all right, this is a nice expression that helps us solve for u and y. So let's go ahead and put this expression directly into practice, okay? So let's solve for u and y. We'll plug that result into our state equation when w is 0, and we'll see what results, okay? All right, so what we had derived above is we showed that we have an I, a minus d22, a minus dk times I, multiplied by this matrix, or excuse me, by this block vector u comma y. Together, this is all going to be equal to a 0, a ck, a c2, and a 0. Oop. Let me write this a little bit neater. Oh my gosh. There we go. Okay. This is going to be multiplied by an x and an xk. And finally, a plus 0, and then a d21 times a w. When we put all of this together, actually, did I remember this d21 up here? I did too. Okay, I just didn't separate them out. All right, back to it. Good sanity check. All right, so what we had claimed is that under this well-posedness assumption, under well-posedness, this is invertible, okay? And remember, this well-posedness assumption is, in fact, equivalent to what we had assumed with this I minus d22 dk non-singular, okay? So we could go ahead and invert this matrix and solve for u and y, right? And what we'll find is that u comma y is equal to this I minus dk minus d22 times an I inverse multiplied by a 0, c2, ck, 0, x, xk, plus 0, because we're assuming w is equivalently equal to 0, okay? All right, so let's go ahead and plug this into our state and output equations, and just our state equations, and see what we get, okay? So if I want to rewrite my state equations, x dot equals ax plus this b1 times w plus a b2 times u. Well, first this w is going to wipe out, right? Because we're assuming that w is equal to 0. So then we get x dot equals ax plus a b2 times u. And then for my controller, I'll get an xk dot equals an ak xk plus a bk times y, because y is my input, right? And I go ahead and I write these in block form. What I get is an x dot, an xk dot will be equal to an a0, 0, ak multiplied by an x and xk plus over here a b2 and a bk, 0, 0 times u and y. Now what do? Well, I just go ahead and I plug in for this uy expression that we solved for up here, okay? So if I do that and I factor out all of these x terms, because I also have an x right over here, what do I find? But an x dot, xk dot is equal to, I'll just put this in parentheses, a0, 0, ak plus a b2, 0, 0, bk multiplied by this inverse, right, which exists because of well-posedness, and I minus dk minus d22 times an identity, inverse multiplied by 0 ck, ck, c2, just a c2, yeah, 0, so much matrices, multiplied by finally an x and an xk. All right, so this is precisely this ACL matrix, right, which we kind of claimed in this theorem above. And what we know is that ACL is Hurwitz, then gives us this global exponential stability condition, okay? So what we conclude is that since I minus d22 dk, being non-singular, is in fact a sharp characterization of well-posedness, and this ACL Hurwitz is a sharp characterization of global exponential stability, we conclude that putting those two things together gives us a sharp characterization of internal stability, okay? All right, so that's a proof. Nice. Okay, so something that you might have noticed so far is that kind of the flavor of these results when we're working with these maybe somewhat complicated interconnected control systems is that things really seem to be pretty algebraic, right? We have these huge matrix expressions, we're inverting all sorts of things, right? We're doing all this kind of crazy algebra, all to make some really pretty simple claims, right? So what we want to see now is really if we could simplify these arguments to something that are kind of a little bit easier to check, all right? So what's next? What we want to do is avoid complex / lots of algebra. Okay? So you want to find easy characterizations of internal stability. All right? Now, let's kind of think about how we might do this, right? We just go ahead and take a look at our feedback system over here, right? We have our system G, we have our system K, which we're kind of analyzing from this I/O perspective in this general feedback arrangement, right? We made these assumptions of stabilizability and detectability, all right? So what does this sort of mean for us? Well, we know that detectability really tells us a lot about our ability to kind of, reconstruct full state information just from output measurements, right? So maybe under some sorts of stabilizability and detectability assumptions, we can actually just come up with I/O characterizations of internal stability, right? Maybe we don't need to analyze this full matrix ACL. Maybe we can get away with something like a transfer function characterization, right? Which, in the past, transfer functions have been pretty convenient for I/O analysis, right? They really simplify out a lot of these different pieces that we just kind of need for I/O systems, okay? So what are we going to do now? Well, in order to simplify this, our strategy, let's use, let's say, stabilizability / detectability ideas plus transfer function ideas to come up with simple I/O tests for internal stability. Okay? Maybe if we do this, we'll really kind of be able to study these properties in a much simpler way. Okay? So what are we going to do, right? Maybe first what we can kind of analyze in terms of, which transfer function we should actually consider is what we think is really the most important factor for internal stability. All right? So if I just go ahead and I write out my state space system once more, I try to figure out what's the best transfer function for internal stability. So I'll write out this x dot equals ax plus b1 times w plus b2 times u, right? And then I have a z comma y is equal to this c1, c2 times x plus this d11, d12, d21, d22 times a w and a u. And then I go ahead and I write out the transfer function of the system, which will map from this w comma u, and it maps to z comma y. Well, this transfer function will kind of be of the form g hat of s will be equal to a couple of different terms, right? If we're mapping from wu to z comma y, then our upper left entry will be a g hat going from w to z of s, right? Then we'll have a g hat going from u into z of s, right? Now in our bottom row, what we'll have is a g hat going from w into y of s, and then a g hat going from a u into y of s, okay? So what part of the system do we think is most important for studying internal stability? Well, if we want to kind of figure out conditions in terms of our controller, right, and how our controller is influencing our system, it seems like the relationship between u and y would be the most important, right? So this g hat uy reveals how the controller interacts with the system, okay? At least in part, right? Because it kind of talks about how any input coming in gets amplified to an output signal. We know that output gets passed through a controller block, which then gets passed back to our input and so on, okay? So here's our idea. What we're going to do is let's zoom in on the relationship between this g hat uy subsystem and the controller block, okay? Okay, all right? So if we do this, maybe we can fully understand how the controller K affects the system and can make a conclusion about internal stability. Okay? So this is kind of our motivating idea, right? We want to kind of consider some interconnection between this g hat uy system and kind of my controller block system. All right, because this g hat uy at least seems to capture what's going on between u and y, at least in part, right, for this full system that we have up here, okay? So this motivating idea leads us to something called an interconnection noise system, all right? Let me go ahead and set this thing out, and I'll kind of explain why we want to focus on this system in just a sec, okay? So definition, this is the interconnection noise system. All right, so what I'm going to say is let's consider a general feedback arrangement which interconnects a plant, right? G equals A, B, C, D, and a controller, which is going to be another LTI system, K equals AK, BK, CK, and DK. All right? So associated with this system, I'm going to define a special subsystem which kind of does this zooming in, which we just discussed up here. Okay? So the interconnection noise system associated with this feedback arrangement is going to be the system which interconnects GUI, which interconnects GUI and K, all right? But it's not just going to do this, it's going to have some extra noise injected, all right? And I'm going to explain why we have this extra noise injected in just a moment, all right? So we're going to have first an LTI subsystem GUI of our original system, right, which just deals with this U to Y relationship. Then we're going to have our controller block K, which is just going to be our standard controller block, all right, nothing different. Now, what are we going to have? We're going to have a couple of summing junctions, right? So these junctions take in signals and then they just kind of add them up, right? So we're going to have this. Whoop. That goes in there. This goes in here. Goes in there. Let me just label a couple of these signals before we talk about this, okay? So I'll call this D1, a V1, a V2, and I'll call this one D2, okay? So what's the basic idea? Well, the idea is that this D1 and D2 represent the cross terms in the full system. So for example, this could be from our W term, right? Because if we go ahead and we look up here, we also get some sort of relationship between W and Y, right? So U is not the only thing that's affecting Y in our true system, right? We're also getting some noise, right? So what we're effectively doing is we're saying, okay, let's zoom in on this subsystem GUY, but we know GUY isn't actually perfectly representing this U to Y relationship, right? So what we'll do is, in order to count for these other terms in the system, we just kind of inject noise, right? Now this D1 will account for one cross term, right? And this D2 will account for another cross term, this time on the input, okay? So D1 gives us the cross terms that are entering on the output signal Y, right? And then D2 will tell us how those kind of propagate through to the input stage, all right? So basically what we're doing, we're zooming in on a subsystem, right? But instead of saying, okay, this subsystem perfectly represents what's going on in my original system, we know it doesn't, right? We know there's cross terms. So to accommodate for these cross terms, we inject in disturbance noise, all right? That's kind of what we're doing in this interconnection noise system. Okay, so this is the basic setup of the interconnection noise system. Now, real quick, I just want to specify what the state equations of GUY are, just so we're all on the same page, okay? So here, this is where GUY is the subsystem of G defined as follows. So we're going to have an x tilde dot of T will equal to an A times x tilde of T plus a B2 times a V1 of T, where V1 is just the signal over here. And then we'll have a V2 of T will be equal to a C2 times an x tilde of T plus a D22 times a V1 of T, okay? So just to note, this is just our standard state equation with the noise removed, right? Or with the exogenous input, W, removed. Okay? So in this case, we're only accounting for this B2 term, and we're only interested in studying kind of the measured output, Y, right? Removed. And also say, and Z removed. Okay? All right, fantastic. And here K is just our standard controller subsystem, okay? Now, just as a quick side note, just to clarify, this B2, C2, and D22, these all just come from our standards G equals ABCD system, right? And how we kind of partitioned that earlier. Okay, so our general claim was that, if we kind of zoom in on this subsystem dealing with the relationship between U and Y, maybe we can make some claim about how the controller affects our entire system, right? Because this GUI system really seems to capture the relationship between the controller and the full system, right? So what we're going to say next is that we can actually get an I/O kind of characterization of internal stability just by studying this little subsystem over here, okay? So this is actually going to be pretty valuable. All right. So first what I'm going to do is I'm just going to kind of state some basic conditions that tell us when this interconnection noise system is well posed and when it's internally stable. Then after that, we'll talk about how we can use this to study the full system. All right? Okay. So let's start off by talking about well-posedness of this interconnection noise system. So lemma, this is well-posedness and internal stability of the interconnection noise system. Okay? So what I'll say is that consider a general feedback arrangement interconnecting a plant G and a controller K. All right? Then the interconnection noise system associated with this feedback arrangement satisfies the following. Well, first we're going to have a well-posedness condition. So what we're going to say is that the interconnection noise system is well-posed. Well-posed if and only if this I minus d22 times dk is invertible, right, or non-singular. Right away, this should jump out to you as the same condition that we had earlier, right? That's kind of interesting. And second, what we'll have is an internal stability condition. Okay? And this is that the interconnection noise system is internally stable if and only if the general feedback arrangement is. Okay, so we're making two claims here, right? First, that the interconnection noise system is well posed if and only if I minus d22 dk is non-singular, right? Which is equivalent to saying well-posedness of this interconnection noise system is equivalent to well-posedness of the general arrangement. And second, we say that internal stability of this interconnected system is equivalent to internal stability of the general arrangement. Okay, so what this lemma effectively tells us is that studying this smaller subsystem from GUI to K with this disturbance noise injected in actually tells us a lot about this overall system. Okay, all right. So let's go ahead and prove this result. So proof, we'll start with this well-posedness result. Now remember, what we want to do is we want to verify that we get unique solutions to the state and output equations, okay? Now in order to prove this, I'll just kind of take the same strategy as before, right? Now over here, we get this kind of algebraic relationship, right? So what we're going to do is we're going to solve these algebraic relationships for V1 and V2. And once we've done that, we'll identify conditions for well-posedness. Okay? Okay. So here's what we're going to do. So we're going to solve algebraic expressions for V1 and V2 to get well-posed conditions. All right. So how are we going to work this out? Well, let's just start off by stating kind of what these signals V1 and V2 are. So based on the summing junction over here, we have that V1 is equal to the output K of the controller block plus D1, okay? So we get that V is equal to U plus D1, all right? But what's the output of our controller block? Or, excuse me, this should be a V1. Well, we get that V1 is equal to what exactly? Well, it's equal to a CK times XK, where XK is the internal state, right? Plus a DK times whatever's passed into the controller block. Well, what's passed into the controller block? Well, it's a V2 plus D2, right? So these two signals are taken in, right? and then they're summed until they come into here, okay? So a v2 plus d2 enters this term. v2 plus d2, all right? And then we're going to add in a d1, okay? So how are we going to solve for this? Well, maybe what we'll do now is we'll do another substitution, right? We also know how to calculate v2, right? Because what's v2? v2 is the output of GUY, okay? We can express that in terms of v1, all right? So now let's substitute v2 is equal to c2 times x tilde plus this d22 times v1, all right? If we go ahead and plug this in, we can get kind of an algebraic equation for v1. Once we have this algebraic equation, we can study conditions for well-posedness, okay? So let's perform this substitution. We get v1 is equal to a ck times xk plus a dk times v2 plus a dk times d2 plus d1. Now let's plug in for v2. We get a ck xk plus dk times c2 x tilde plus a dk times a d22 times v1 plus a dk d2 all plus d1, right? Okay, so we have a v1 over here as well. Let's collect all the v1 terms and figure out what we need to get a unique solution. Okay, so if we collect on the left-hand side and factor out, we'll find we get an I minus dk d22 times v1 is equal to the ck times xk plus dk times c2 x tilde plus a dk times d2 plus a d1, okay? So if we want to be able to uniquely solve for v1, this is necessary and sufficient for well-posedness, okay? Or, excuse me, the invertibility of this is necessary and sufficient for well-posedness, okay? Because if we can invert this, right, then we can go ahead and uniquely solve for v1. Once we have v1, we can uniquely solve for v2, right? Once we have v2, then we could uniquely solve these state and these output equations, all right? So unique solution for v1 gives a unique solution for v2, which then gives us a unique solution to the full state and output equations. Okay? So then all of this effectively tells us that I minus dk d22 is invertible if and only if the system is well-posed. Okay? So that goes ahead and gives us a proof of our first item over here. All right? Great. So now let's talk about the second item, which says that this system is internally stable if and only if the full system is internally stable, right? Now there's a couple ways of verifying this, right? What we can do is we can go ahead and solve for the full state and output equations, right? So we could solve for the full state and output equations and get an A closed loop matrix, right? Kind of similarly to what we had done before. Or just kind of the proof sketch version, we notice that the A matrices are the same for GUY and G, right? And then AK is the same as before, right? Because we don't modify the controller block. So then kind of our loose argument is that, the A matrices are the same for the GUY and G systems, and AK is the same. So we can effectively argue for global exponential stability of xk in this manner. Okay? So just as a side note, this is hand wavy, but this is effectively what you'll get from this rigorous argument, okay? So I just want to eliminate doing all of this algebra because it's a little bit messy, all right? So our general argument is that well-posedness follows from this algebraic condition, which we derive from the output equations, right? and it turns out to be the same well-posedness condition as before, right? And then internal stability, we can kind of argue in this hand-wavy manner. Internal stability is equivalent because the A matrices are the same and the full state vector is the same, okay? Now, if you want to be fully rigorous, obviously you need a more formal argument than that, but it just involves a lot of algebra, okay? All right, there's nothing too crazy about it. Okay, so that effectively tells us that this interconnection noise system, right, is a smaller system, right? It's a subsystem, but it still gives us a really sharp characterization of these kind of different properties that matter in our full system, all right? So it's a simpler system, but still characterizes our overall system. Okay. So this is valuable, right? But remember, what we were trying to look for was maybe a transfer function characterization of internal stability, right? Because transfer functions, they're really easy to understand stability for, right? You just evaluate kind of the roots of the denominator, and then you're pretty much good to go, right? So how are we going to figure out a transfer function characterization of internal stability? Well, it seems like an obvious transfer function to check is the transfer function going from d1, d2 to v1, v2 in this system, right? Because effectively, we're checking how this interconnection noise amplifies these internal signals in this interconnection system, okay? So if we can prove that that transfer function is stable, right, given we have internal stability, maybe we could actually get a complete characterization of internal stability of the full system, all right? So what I'm going to say next is this is true just under some basic additional assumptions on detectability and stabilizability, okay? All right. So this brings us to a theorem, which is the transfer function characterization of internal stability. All right. So what we'll say now is suppose that A comma B2 is stabilizable, and that A comma C2 is detectable. So this is in addition to our usual assumptions. Okay. So remember, usually we assumed that each of these state space models was stabilizable and detectable, right? Now we're just assuming a similar property, but for this subsystem GY, okay? All right, so under these assumptions, what do we have? Well, then we have that the general feedback arrangement is internally stable if and only if the transfer function from d1 comma d2 going to v1 v2 in the interconnection noise system belongs to the space RH infinity, right? Which is the set of stable, proper, real rational transfer functions. Okay, so if the transfer function going from d1, d2 to v1, v2 in this interconnection noise system is stable, proper, and real rational, right? In fact, we're already guaranteed real rational and proper, kind of based on well-posedness and the fact that we're working with LTI systems. So really, if this transfer function is stable, then we're guaranteed to have internal stability of our full system, provided we also have the stabilizability and detectability assumption. Okay, so this is really nice, right? We only need to check one transfer function to actually characterize internal stability of the full system. This is a reasonably powerful result, right? Okay. So I'm just going to go ahead and kind of give you a proof sketch of this. Again, as I've kind of remarked a couple times in this lecture, these systems often have a lot of messy algebra involved, right? So I'm just going to cut to the chase because that algebra isn't particularly revealing. Okay, so let me give you a proof. This is going to be a sketch of a proof, okay? So what I'll first say is, for convenience, I'll just go ahead and define a matrix D bar equals an I minus dk minus d22 and I, okay? So remember, that's that same matrix that we kind of had earlier to determine well-posedness, all right? So what you can do is you can go ahead and you can calculate the transfer function of the system from d1, d2, going to v1, v2, all right? And this is a really big expression, right? So it's going to take a little while to write. And if you go ahead and you kind of work all of this out, what you'll find is that if you work out a v1 hat of s, right, which remember is just the Laplace transform of v1, this v2 hat of s, you'll find that this is equal to this d bar inverse multiplied by a 0, a ck, a c2, and a 0, all multiplied by si minus ACL, right, where ACL is that closed loop matrix we derived a little while ago in lecture, right, for the full system. ACL inverse multiplied by this B2, 0, 0, BK, multiplied by D bar inverse plus a D bar inverse plus a 0, 0, 0 minus identity. Okay, I think this should all be correct. Okay, all multiplied by a D1 hat of S and a D2 hat of S. Okay, so this entire thing in here, this is the transfer function from D1, D2 going to V1, V2. Okay, so it's a huge transfer function, right? And our claim is that this should entirely characterize internal stability of the transfer function. Okay, so let's call this transfer function W hat of S for convenience. Okay, so how do we figure out the relationship between W hat of S and internal stability? Well, what do we see? Well, let's say, suppose the general feedback arrangement is internally stable. Okay, so this implies that ACL is Hurwitz, right? What does that tell us about the poles of W hat? Okay, so what we notice is that the poles of W hat are the poles of this block over here, right? 0, CK, C2, 0, multiplied by SI minus ACL, inverse times a B2, 0, 0, and a BK. All right. Now, why is this? Well, this effectively follows from the fact that poles are where transfer functions kind of blow up, right? And what we have over here is this is the only piece of the transfer function that involves S, right? Now, these D's are invertible, all right? So they won't affect blow up, right? Because they have full rank, right? So what we effectively conclude is that, if we have a pole of our system, well, it's going to be a pole of this little piece over here, okay? So what we find as a result of this is that the eigenvalues of your matrix ACL, right, which is where we get blow up, this set contains all the poles of this transfer function W hat of S, right? Because eigenvalues of the system are actually exactly where SI minus ACL inverse blows up, right? Because at an eigenvalue of ACL, this inverse becomes ill-posed, right? Okay, so we see eigenvalues of ACL means W hat needs to blow up, right? And provided W hat blows up, we have a pole, okay? So what we see in one direction, eigenvalues of ACL are a strict superset of the poles of W hat. Okay? All right, so that gives us one direction. So if we're Hurwitz, this goes ahead and implies W hat is stable. Okay? From there, we can conclude that it belongs to RH infinity. Okay? So that's one direction. Now, in the other direction, what do we do? Well, let's say, assume the poles of W hat of S are stable, right? Or, W hat of S belongs to RH infinity, okay? What else can we say? Well, what can we conclude about the eigenvalues of ACL? Well, let's just go ahead and take a look at this same matrix expression which we derived up here, right? There's two possibilities that could occur, okay? So first, we get an eigenvalue that is a pole, okay? So in the event where we get an eigenvalue that is a pole, it must be stable, okay? So that's good, right? Now second, what if we get an eigenvalue that's not a pole? Well, what this means is that we get a cancellation in the transfer function of the factor involving that eigenvalue. Right? It just means that it kind of cancels out in this product 0 ck c2 0, right, times si minus acl inverse times a b2 0 0 bk. All right? So it just kind of gets canceled out and we don't end up seeing it, right? But what does that mean? Well, something that we kind of know about these systems, right, is that cancellation corresponds to loss of controllability or observability, okay? So whenever we get a cancellation, that means that that particular mode of our system is either uncontrollable or unobservable, right? But what we assumed under our stabilizability and detectability assumptions, we assumed that all unobservable / uncontrollable modes are stable, okay? So this follows from stabilizability / detectability. So what we effectively conclude is that if we have an eigenvalue of A that's not a pole, that means that a cancellation will occur in this expression, right? And since we assumed that A, C2, and CKB, and so on and so forth are all controllable and observable pairs, where this will effectively land us up after some reasoning is those need to be stable, okay? And this follows from the stabilizability / detectability assumption, okay? All right, very cool. Okay, so just to clarify, this does take a little bit more kind of reasoning than this. You can kind of go ahead and do some kind of pole placement arguments to kind of make this work a little bit more rigorously. But this is the basic idea, okay? We're effectively using this idea of pole zero cancellation just to kind of work with reasoning about the eigenvalues of ACL, okay? So some more reasoning makes this sketch idea rigorous, but cancellation is the key idea, okay? All right. So I'll go ahead and leave it at there. Thanks for watching.